So this is lecture number 3 in this series on microprocessors. In the last session, we studied how we studied the pin diagram of microprocessor 8085, and we studied some of the pins. So far, we have studied pins 1 and 2, uh, pins 1 and 2, at which the crystal oscillator is actually located, and this crystal oscillator basically sets the internal clock frequency of the microprocessor. We studied pins 12 to 19, AD0 to AD7. These are bidirectional pins used for two purposes. One, to carry the data, that is actually bidirectional in nature, and two, to carry the least significant bits of the address lines. So these work in multiplexing mode on the base of time sharing mode, and AD0 to AD7 carry the least significant bit of the address. As we have said, that address is basically a 16-bit data, and the rest of the 8 bits are carried by lines 21 to 28. That's A to A15. They carry the most significant bit of the address line. So this will be a unidirectional. These will be unidirectional, A to A15, because they do not have to carry the data. They only have to carry the address. We studied pins 20 and 40. Since microprocessor requires plus 5 volts to operate 8085, so plus 5 volt will be applied through pin number 40, and the ground will be applied across pin number 20. Also, we studied clock out signal, that's 37, to interface the external circuits and interface the external devices and synchronize them with the microprocessor 8085. We use the clock out signal. It will actually the 3.14 megahertz of signal will be actually available at this pin. So moving on, before we study other pins, we need to understand we'll be doing this in detail also. We'll be doing the timing diagram of microprocessor, and it will actually take a while before we grasp the entire timing diagram of the 8085 microprocessor. But here I want to explain to you the states of existence. So there are actually 10 states of existence for a microprocessor in which it actually remains. These are numbered as T1, T2, T3, T4, T5, T6. These states of existence last for only one clock cycle. That's for 3.14 megahertz, 1 by 3.14 megahertz. That's approximately 0.32 microseconds. Fine. So each of these states will only last for 0.32 seconds. So the microprocessor can remain in these states for only 0.32 microseconds. What is actually T1, T2, T3? I'm not going to be discussing that right now. And apart from this, you have other states in which the microprocessor remains. T reset, T hold, T halt, and T wait. So these are other 4 states of the microprocessor 8085, in which T reset, T hold, T halt, and T wait. So these timing, the microprocessor can remain in these states for integral number of clock cycles. So it can be more than one. A microprocessor can remain in this state for more than one clock cycle. That's for more than 0.32 microseconds. Integral values of time rather. So the microprocessor can remain in either of these, can remain in any of these 10 states at a time. It can either be in states T1 to T6, or it can be in the states T reset to T hold, T halt, and T wait. As I said to you, we'll be discussing these things in detail: what T1 is, what T2 is, what T reset, T hold is, and why T1 to T6 is only lasts for one clock cycle, and what the others, these four T states, actually last for more than one number of integral cycles. We'll be doing this in detail. Now, as we understand some terms here: reset, hold, halt, and wait. Simply linguistically speaking, we can understand what actually the microprocessor might be doing in these states. Fine. So, depending on this, we have pin number 3 and 36. Pin number 3 is the reset out, and pin number 36 is the reset in with the uh, with the bar on the top. This actually means it's a complement here. Fine. So whenever the signal will be at reset in pin, whenever the signal at reset in pin is made low, that means the signal actually will be high because it's a complement there. The microprocessor, wherever it is and whatever it is doing, will exit that state and enter the T reset state. Fine. So pin number 36 is T reset, is the reset in pin. Reset in, it's reset in pin, and it has been shown to you with the bar at the top. That means actually this will be active when the pin will be low. Fine. So if we are applying low signal to this pin, that means zero signal to this pin, pin number 36 will actually be having will be actually high at that time. It will be active at that time, and the microprocessor, wherever it is, whatever it is doing, it will exit that state and it will enter the T reset state. Fine. So the microprocessor basically will perform a number of actions in this reset states. One of the actions that actually the microprocessor performs is that a high signal is issued to the reset out pin. Fine. Which results in all the peripherals that will be connected to the microprocessor to be reset as well. So whenever T reset is active, pin number 36 is active, pin number 3 is also becomes active. That means reset out becomes active. Reset out means all the peripheral devices that are interfaced with the microprocessor will also become active. If pin number 36 is active, and by active I mean it is actually active at the low state. Pin number 36 is active for low state. That's when 0 is applied to it. So pin number 3 reset out also becomes active. One, reset in will reset the microprocessor, and also it will reset all the other peripherals that are actually so reset out pin, it resets all the peripheral devices. That means it will tri-state also all the apart from this, all the buses will be tri-stated. So during this state, the peripheral devices are reset, the buses are tri-stated. It also resets the halt flag. Fine. In the program counter that we are actually studying later on, program counter, you can basically see the address 0000H is actually uh, assigned to the program counter. Uh, all the control signals are tri-stated. These are various actions that the microprocessor performs during the reset state. So some of these you might understand straight away, some of these you might not. But we will be going through all of these things. Fine. It disables all maskable interrupts. So the course of this semester will be actually understanding various things, and we'll get to know all of these things. We'll be actually doing in detail the T reset, what happens during the T reset state in a later stage, at a very later stage, because we do not know right now. I cannot tell you what is a maskable interrupt. I cannot tell you straight away what a program counter does. Fine. So all these things we will be studying, and but these are the things that happens during the T reset state. The microprocessor is no longer performing its normal task. It enters the T reset state, and some other functions overtake the microprocessor. Fine. So pin number 36 and pin number 3 are used to reset the microprocessor as well as the peripheral devices associated with the microprocessor. So we have done pin number 3 as well as pin number 36 now. We have pin number 6 to 10 trap, uh, pin number 6 to 10. Pin numbers 6 to 10. You have trap, you have RST 7.5, RST 6.5, RST 5.5, and INTR. These are all interrupts. These are referred to as interrupts. Now, they are actually again externally initiated signals. So, any external device can actually interrupt the normal working of a microprocessor and overtake its usually running programs. If a microprocessor is doing some arithmetic programming, say for example, it's doing some program, and all of a sudden, because of the priority of the out the priority set by the external device, it will interrupt the microprocessor. Fine. Again, this will be studied in detail at a later stage, but right now, linguistically, even if you can understand, interrupt is something that basically interrupts the normal flow of the microprocessor. So these pins will be used to interrupt the microprocessor. They have certain priorities that we'll be discussing, which of them has the highest priority, which of them has the lowest priority. So that means actually some of them may be able to interrupt the microprocessor straight away, some of them may not be able to interrupt the microprocessor straight away. Apart from these, what are other interrupts that the microprocessor can have? We'll be understanding that. So these are externally initiated signals, and uh, simply stating, your microprocessor is interrupted because of some external device, because of some other priorities that the microprocessor has to handle first, and it has to exit the uh, usually performing task that it was assigned. That's pin number 6 to 10. These are interrupts. They have priorities. We'll be discussing that. Then you have pin number 39. Pin number 39, it's the hold. So as we have seen from the timing diagram, T states, there is one state also, that is the hold state, T hold. So in this, the microprocessor will actually enter the T hold state, and what happens? Uh, so what happens in this case is that Again, it's an externally initiated signal. So an external device like a DMA, direct memory access, can be actually uh, asking for the control of the address lines as well as the data lines of the microprocessor. So this state is initiated when hold is actually enabled. Similar in associated with this is also pin number 38, HLDA. HLDA is hold acknowledge. Again, this is a externally initiated signal. So this signal basically acknowledges the hold request. So in this state, in the T-hold state, the direct memory access uh, to any external device basically allows the to override the microprocessor and take over its address lines and control and its data lines. And to acknowledge this, we have the this pin number 38 and pin number 39. Fine. Uh, so both of these are again externally initiated signals. Pin number 6 to 10, they are also externally initiated signals. Pin number 36, reset in, it's also an externally initiated signal. Uh, so we are done with pin number 38 and pin number 39 also. Pin number 39, pin number 38, both are externally initiated signals. Pin number 36 is an externally initiated signal. Pin number 3 is outgoing signal rather. And pins 6 to 10, they are also externally initiated signals. Then you have actually pin number 35 ready. Again, the system will be put in the this is also an externally initiated signal. So what happens is with pin number 36, as far as pin number 36 is concerned, that is the ready signal. During this, the microprocessor, which actually maybe interface with an external device, will try to make itself compatible with it. Fine. The external device can be slower as compared to the microprocessor. To make sure that it comes in synchronization with the program that's with the execution of the microprocessor, we have to wait for this peripheral device to actually catch up. So the ready pin basically makes the peripheral device a slower peripheral device compatible with the 8085 microprocessor. So makes the slower peripheral device compatible with 8085. So normally, if the signal is zero, that means the microprocessor is not ready yet. It will have to wait until the ready pin is basically becomes equal to 1. If it is high, that means now the your outer device is actually ready and for execution, and it is now compatible with your microprocessor. So you can have a slower peripheral device attached to the microprocessor because of its uh, slower processing as compared to 8085. We will have to wait, the microprocessor will have to wait for it. So until the ready signal is zero, it actually indicates that peripheral device is not yet ready. As as soon as the signal becomes one, that means the peripheral device is now ready. And every time this ready signal is actually checked in the T2 state of the microprocessor. Right? we'll be doing that again later on. So pin number 36 is used to check the readiness of the microprocessor. So we are also done with pin number 36 here. Now there are these signals 34, 33, 32, 31. So these are known as control and control signals. Pins, control and status signals rather. We have among these control and status signals, first you have ALE, the address latch enable. Address latch enable here is the pin number 32. Pin number 30. Address latch enable. Fine. So every time the microprocessor will actually begin the operation, the very first thing that the microprocessor needs is to fetch the address of any device. So address latch enable actually enables the address to be fetched. So this signal is primarily used to latch the lower order address from the multiplex bus. Fine. And then it will actually generate a separate signal for fetching the address from the fetching the most significant bits of the address. So ALE high will be checked at every time the microprocessor begins the execution. ALE will be checked, address latch, and it will fetch the address from the address buses, that's 12 to 19, that's the least significant bits of the address, and then after that it will be actually fetching the address from the most significant bits of the address. So this will be done every time, because every time the microprocessor will have to see which what is the address to which from which the execution of the program will begin. Fine. So in T1 state, in every T1 state is actually the you can say to the first state of every programming cycle. So every time in the T1 state, the microprocessor will issue a high address latch enable signal, that's ALE will become 1, which is actually derived from the clock signal, and it will actually remain in this state. As I said to you, T1 state lasts for only 0.32 microseconds. So it helps us to hold the least significant bit of the address from AD0 to AD7. Fine. From pins 12 to 19, we can get the address by enabling the address latch, because these buses are used for dual purposes. They are used for carry address as well as the data lines. So we need to make sure it's working in the to make it work in a multiplex mode, in a time sharing mode. We need to make sure that these lines are either used for carrying the address or data. So A will make sure of it that in the T1 state, this is used to actually fetch the address, so that the least significant bit of the address can be obtained. While as far as the uh, address available from A8 to A15 is, it will always be available to us at the output, because the purpose of A8 to A15, that pins 21 to 28, is only to carry the address. But pins 12 to 19, they have to carry both the address as well as the data. We need to make sure that these pins are working in the multiplex mode, in time sharing mode properly. We need to make sure that we are able to separate the time for which only it carries the address, and separate the time for which it only carries the data. So in T1 state, every time the address latch enable will be 1, so that these buses can be used for as address lines at that time. So this is the purpose of pin number 30. Then you have pin number 32 and 31. Read pin number 31. Write again pin number 32 and 31. You see there is a bar at the top of read and write. That means they will be active for low states. So what happens during these with pin number 32 and 31 is that pin number 32 will be actually the read control signal, and the pin number 31, that's WR, will be the write control signal, and they will be active when they will be active low actually. Fine. So if this pin is 0, that means it's active. That means the memory or whatever is interfaced, the IO device, whatever is interfaced with the microprocessor, is ready to be read. And similarly, if write becomes 0, that means it becomes active. So it means memory or the IO is ready to be written on. So pin number 32, when it is high, that means when it is high, when it is actually low, this pin is enabled. That means it is active. So it will make sure that it actually indicates that the memory or the IO device that is associated with the microprocessor is ready to be read from, and pin number 31 actually indicates that the memory or the IO device is actually be ready to be written onto. Fine. So will be using the data bus for reading and writing the writing from the microprocessor, from the memory or the IO device. Then you have pin number 34. Pin number 34 is IOM bar. So if it is 0, it means that memory is accessible. If it is 1, it means IO, that's the input outputs that are interfaced with the microprocessor, are accessible. Now we have to write onto the memory or read from the memory. Similarly, we have to write onto the IO device, input and output devices that are interfaced with the microprocessor. We have to write onto them or to read from them. So IO by M bar, if it is low, that means actually memory is high at that time. So memory will be accessible. It basically differentiates between the memory and the IO device. It tells you where to read and where to write to. Fine, where to read from and where to write to. So this operation helps us differentiate between the memory and the IO devices. So if it is 0, that means memory is actually accessible to be written onto or to be read from. If it is high, that means actually the IO devices are ready to be written to or read from. Then you have SOD and SID. We actually also have pins number 29 and pin number 33. These are also status signals, pin 29 and pin 33. SO and SI, S0 and S1. Fine. So these two signals are the status signals of a microprocessor. So they are similar to what actually the pin number 34 does. That's define the status of a microprocessor. There are a number of purposes for which the machine will be machine will indicate the status of the system. Like it may be used to indicate whether the machine is in halt state, whether the machine is in hold state, whether the machine is in reset state, whether the machine is in memory read state or the memory write state, whether the machine is in IO read state or the IO write state, or it's doing whatever the state of the microprocessor is. That state is actually reflected by these two signals, gives the status of microprocessor. So along with the pin number 34, pins 29 and 33 basically give us the status of the microprocessor. It will actually help us indicate in which these three in combined will actually help us indicate in which state the microprocessor actually is presently. Fine. So depending upon whether SO is high or SO is low, SI is high or SI is low, IO by M bar is low or high, we can differentiate between different states of the microprocessor. As I said to you, it can be either halt, hold, reset, IO read, IO write, memory write, depending upon the status of these signals. Fine. Normally, for the read operation, whether it's from the memory or from the IO device, S1 is 1 and S0 is 0. For the write operation, S1 is 0 and S0 is 1. Fine. This is 1 for write operation. This is 1 for read operation. So we'll be checking the status of these signals in every time we'll be executing a program. We'll be checking the status of these two signals, and to indicate whether we are writing right now or to indicate we are reading right now from the memory or from the IO device, we'll be checking the states of SO and S1. Fine. Now we are left with two signals, that's 4 and 5, SOD and SID, pins number 4 and 5. They pin number 4 and 5. These are SOD and SID. That's actually meant for serial operations, performing serial operations. So SOD, that's pin number 4, is serial output, and SID is serial input, that's pin number 5. So for carrying out serial transmission, as we discussed earlier also, there is two modes of transmission, whether it can be a parallel mode of transmission or a serial mode of transmission. Normally the microprocessor in itself uses the data lines AD0 to AD7 to carry out parallel transmission, but some some interfaces can be communicated serial wise. So to transmit with them, to carry out serial transmission with some peripheral devices, SOD and SID are used to send the data over one bit at a time. Rather than sending 8 bits of data together, we'll be sending out one bit of data at one time. Whether now it's a input operation or an output operation, accordingly you'll be using pins number 4 and 5. So that's about the pin diagram of microprocessor 8085. So looking at the pin diagram once again, we have studied pins number 1 and 2. X1 and X2 are used to incorporate the crystal oscillators to set the clock frequency of this microprocessor 1 and 2. Reset out, pin number 3 is actually associated with the reset in pin 36. Reset in pin is an active low pin. That means it will be active when it is equal to 0. It will actually reset the microprocessor, and there are a number of operations that I have defined what happens basically during the reset operation, and one of them is actually reset out becomes 1. That means actually the output peripheral devices are also reset. Pins 4 and 5, they are used to carry out serial transmission, either output or input. Pins 6 to 10, they are actually the interrupt signals. Pin number 11, it's INTA. I forgot to discuss that. It's actually interrupt acknowledge. Just like we need to actually acknowledge that interrupt is actually enabled at this time. We'll be using this pin. Fine. And AD0 to AD7 pins 12 to 19, they are used to carry both address as well as data. They'll be using these lines in time sharing basis, on a time sharing basis in the multiplex mode, and that time sharing basis will actually be decided uh, for the microprocessor. Pins 20 and 40 are the power supply to the microprocessor. 21 to 28, they are exclusively meant for carrying the address bus. Pins 29 and 33, S0 and S1, they basically define the status of a microprocessor, whether it's a read operation or a write operation, whether it's a halt operation, a hold operation, extra. Pin number 30, address latch enable, is used to enable the pins 12 to 19 to carry the address of the microprocessor rather than to carry the data bus. Pins 31 and 32, they are meant for read and write operations, and they are actually low signals or pins. Pin number 34 is IO by M bar. IO by M bar basically it actually helps us differentiate whether whether the memory is actually accessible right now, or the external interface that can be either an input device or an output device is accessible right now. Pin number 35 basically helps us uh, make a slower outer peripheral device compatible with the microprocessor. Uh, if it is 0, that means the outer device is not yet ready. If it becomes 1, that means the outer peripheral device now becomes ready. Pin number 37 helps us interface and synchronize the output devices. It actually, the 3.14 megahertz of frequency is actually available at this pin. HLDA, hold acknowledge. If system has to be put in the hold state, we need to acknowledge that. In pin number 39, the system is in hold state, and pin number 40, we have already discussed that. So this is about the pin diagram. How what basically different pins do. Some of these operations we may have, some of the operations you most of the operations actually you have not understood yet, because not we do not know how interrupts work. We do not know how a machine uh, reads, or how a microprocessor reads or writes. We do not know about serial transmission. We do not know about any of these states, T states, hold, halt, ready, extra. Uh, we do not know even what a program counter is, where actually the microprocessor stores the address and where from it locates the address. So most of these things are still unknown to us, but we'll be now understanding them one by one. But this is about the pin diagram of the microprocessor. What basically the 40 pins of microprocessor 8085 do. Uh, Now we'll be taking them one by one. We'll be understanding the operation, all these operations one by one, interrupts, DMA, the address lines, how they are actually fetched, how a data is written or read, how the machine is interrupted, how the external devices are interfaced with this system. All of that will be understood throughout this course of on microprocessors. So that's all for